Okay, so here we are with again the 2021 VCAA Specialist Maths Exam 2, the Section B, and we're on question 5 on this particular video. All right, so we've got a mass on an inclined plane, we've got another mass hanging over it, and we're going to have a look at what's going on with this. So the plane's 30 degrees, as the information says there, light inextensible strings, so we don't need to worry about any mass there. Frictionless pulley, so no friction on the pulley, and passes over. All right, so there we go. All right, so in the first part, given that the inclined plane is smooth, find the relationship between M1 and M2 if the mass moves down the plane, mass M1 moves down the plane at constant speed. All right, so I'm going to use down the plane. So first of all, the resultant force is our mass times our acceleration. And what we're going to do is look at the forces that are acting. Now I'm going to, for this one, I'm going to use down the plane as being the positive direction, because this is connected by a string. M2 is going to move in the positive direction, but on M2 has a weight force, M2G, and so that would be acting in the negative direction. All right, so mass 1, of course, mass 1 has a weight force itself, which is M1G. All right, and of course, if we then break that up into two components, we've got one component, this one here, acting down the plane. So M1G sine 30 minus M2G, and that's got to equal 0 because constant speed. All right, so we're after a relationship between M1 and M2. First of all, sine 30, of course, is a half, so that's a half M1G, and I'm going to move the M2G over here. The G's will then cancel, and if I times both sides by 2, mass 1 is twice of mass 2. All right, so the masses are now placed on a rough inclined plane, with the light extensible string passing over a frictionless pulley in the same way as shown above. Let N be the magnitude of the normal reaction force of M1 by the plane, and the resistance force of gamma newtons acts and opposes the motion mass M1. And now in part B, mass M1 moves up the plane. All right, so mark and label all the forces acting on this mass. So this mass refers to mass 1. Now, I've already drawn one of the forces on mass 1. That's its weight force. There's the force of the string, the tension force in the string pulling it up the plane. There's the interaction between the plane and the mass, which is my normal reaction force. So of course, you'd be using a ruler. And then because it's moving up the plane, friction opposes the motion. So friction is there. All right. So that's gamma resistance force magnitude gamma newtons. So I probably don't need that N there. So let's, all right, there we go. So mark and label. And so, what does it say? Mark and label a force acting on this mass. So there I have. That's what we need to do, all of those forces. All right, taking the direction up the plane is positive. So up the plane is positive. Find the acceleration of mass 1 in terms of mass 1, mass 2, and gamma. All right, so again, it's the resultant forces is our mass times our acceleration. And so the resultant forces, so up the plane is positive. All right, so what have we got? We've got this mass here pulling down, so that's in the positive direction. The friction force is in the negative direction, and this component down here of the weight force is also in the negative direction. So we have M2G we have minus a half M1G, that's that component here, that component there, which we worked out in part A. And what we've got is the gamma. Gamma minus gamma n. I do need the n. I've just let n be the magnitude of the normal reaction force. So it's gamma n. So I do need the n here that I took out. All right, and what is that n? Well, that n is equivalent to this component, which is the weight cos 30. All right, and we'll get to that. And that is because it's moving, it's equal to the mass. Now we need the mass of the whole system there, which is what we've got. All right, so then what have I got? I've got M2G minus a half M1G minus gamma times, well, that's root 3 on 2, M1G for our normal reaction. All right, M1 plus M2G. A, not G. What am I doing? Silly, acceleration. Mass times acceleration. Acceleration's not G. Sorry about that. So mass times acceleration. Acceleration. All right, we want to know what the acceleration is. All right, let's, if we put a whole bunch of this stuff together over the denominator of 2, then what we'll have is 2m2g minus m1g minus gamma m1g, and that's all over 2. And then when I rearrange and divide both sides by m1 plus m2, I then get the acceleration. All right, so there's our acceleration expression for the acceleration of that mass. All right, then sometime after the mass is going to move, mass 2 hits the ground at 4.5 meter per second. Whoops. Sorry about that, dropped my pen. and the string becomes slack. At this instant, mass 1 is at point P on the plane, this one here, which is 2 meters. I think it says 2 meters, which is 2 meters from the pulley. So 2 meters from the pulley, take the value of gamma to be 0.1. All right, so if the acceleration now is changing because mass 2's hit the ground, so it's no longer applying a force. We don't need to go all the way and have a look again, but the acceleration changes too. What we can actually do is just look at what we did previously. So this is what was previously. But now this mass 2 has hit the ground. So any term in the expression that has m2 is no longer needed, because that's no longer applying a force on that string. So it's only mass 1 that's involved in applying the force to the motion. So our acceleration then becomes equal to negative m1 minus root 3 times gamma, which is 0.1 m1 g over 2m1. All right, so our acceleration then would be negative, because mass 1 can come out as a common factor and cancel with on the bottom. So minus 1 minus 0.1 root 3 g all over 2 is now our acceleration. So we've got our u. We're told it's going at 4.5 meters per second. We want to know how far the mass travels before it starts to slide back down the plane. So before it starts to slide back down, instantaneously, the velocity would be 0. So using v squared equals u squared plus 2as, constant acceleration formula, which you will have to have in your bound reference. Putting in the numbers. Here we go. On 2 times s. Use your calculator and the solve function in your calculator. Correct to 2 decimal places, we get 1.76 meters. All right, so next, find the time taken from when the string becomes slack for the mass to return to point P. Right, so what's going to happen, I'm just going to go back the page. So what's going to happen, it's at P, the string's slack, it slides up, stops, and then it slides back. So we need the time up to here till it stops, and then the time it takes to slide back. So I'm going to split it into 2 parts. Alright, so split it into 2 parts. So P to highest point. And we've got some information. We know that U at P is 4.5. At the highest point, V is 0. We just found out how far it takes, and then we want to know the time. So using S equals a half U plus V times T, putting in 1.76 equals a half 4.5 plus 0 times t, getting your calculator out and using the solve again, you find that to the top it's 0.7822 seconds. All right, so then we want to know, get back to P. And the thing when we're going back to P is that the friction is now up the plane because it's moving down the plane. So friction now up. So what we know is that the distance it's going to travel, well, it's back to P, it's going to travel a distance of 1.76, but it's traveling down, so it's negative 1.76. U, it was momentarily at rest, and we need to know about the acceleration. And so when we go and look at that acceleration that we had before, this one here we had a plus, so that was the friction, this component here. But now the friction's now up the plane, so all we need to do is change this negative here into a positive. So because the friction's now up the plane, the acceleration is -1, so that's the bit that's due to the weight force, the component of the weight force, and then the friction is now up the plane, so it's now in the positive direction. So that's why we've got that plus there. All right. So now we've got, you can use S equals UT plus a half AT squared, putting in the numbers of -1.76 equals U, which is 0 times T, plus a half times that acceleration, so -1 plus 0.1 root 3 on 2, forgot me G, times T squared. Now, of course, this component here is, or that term I should say, because it's 0 times, so we've now got 1.76 equals a half. I'm going to put some things together because what I have to put in the calculator, 0.1 root 3, I need to use, because we're told decimal places, nearest tenth of a second, so I need to put 9.8 in for G. Got those two multiply together, give me 4T squared. And then now we need to use our calculator and solve for the T. And of course, T is only in the positives, 932. And so now our total time, all right, so our total time is the 0.7822 plus the 0.932. And when we do that, what we end up with is 1.7143. And we were asked to the nearest tenth of a second. Yep, there it is. So to the nearest tenth of a second, it's 1.7 seconds. All right. So there's the end of that particular question. Again, you need to spend some time thinking about it, reading carefully. So reading time, you would initially do that then. And then when you come back, just be very careful and try not to rush through that question.